And we're here today to help, we're here today to listen to Fran Bagnall talk about why planetary science needs space probes. So Fran was born in Dorchester and grew up in Cambridge, England. Turn this up a little bit. She did her PhD at MIT and also did a postdoc at the Imperial College in London. She's now a professor at the University of Colorado Boulder, and she's also a research scientist at the Lab for Atmospheric and Physical Space Science. So Fran has been very involved in a number of influential projects. For starters, she was involved in the Voyager missions, which went out to the outer solar system and were the first space probes to explore the outer reaches. After that, she was involved in the Galileo mission, which was a probe specifically sent to investigate Jupiter and its moons, and is the reason why we have basic estimates and understandings of the composition of Jupiter. More recently, she's been involved in the New Horizons mission, which last year flew by Pluto and gave us brilliant images of its surface. And this year, she's involved in the Juno mission, which is estimated to enter orbit around Jupiter any day now, I guess. And she'll tell you more about both of those things. Now, Fran has had a huge influence on society today, although a lot of you may not realize it. Maybe as a simple example, if you go into Google and just type in Jupiter, the reason why we have that brilliant image of Jupiter is not because we looked through, took a selfie of it or something like that. It's because we physically sent a space probe to there, took a picture, sent the data about 1 billion kilometers back to Earth. And that's a really hard job to do. And Fran and her research science team helped out with that. So before I introduce her, then I just have one or two announcements. So after the show, there's going to be a couple of planetarium shows that people can sign up for. So at the reception table, then you can sign up for that if you want to. There's shows at 9:30, 9:45, and 10. And also, before the end of the show, we're also going to give you some 3D glasses, and I'd ask that everyone please handle them with care, and also make sure you return them to someone in a red shirt by the end of it. So without further ado, let's figure out why planetary science needs space probes, and welcome Fran back onto the stage.
Thank you very much. Great. Okay. So the answer to this question, why planetary science needs space probes, is extremely simple. We got to get up close. And we can have great telescopes, we can do all sorts of stuff with great telescopes from Earth or Earth orbit, but there's nothing like getting close. And indeed, there's nothing like observing from behind or on the top and sideways. So this is particularly important for a bunch of space missions, and I'm going to tell you about two of them. The Juno mission to Jupiter and the New Horizons mission to Pluto. So let's start off with Juno, and it goes into orbit around Jupiter with a bit of luck, every finger and toe crossed as much as I can, on the 4th of July of 2016. So that's the plan. We hope this will happen. Let me tell you a bit about this mission. But first of all, why do we need to go there? We have this great view of the planet with its clouds and great red spot and so on. And indeed, the Cassini spacecraft that flew by in 2000 on its way to Saturn took this great movie where you see the white ammonia clouds going one way and the darker clouds colored by sulfur, which seem to be deeper, traveling in the other way. So we know a lot about the clouds, but we have a lot of questions about the interior. We don't know what's below the clouds. Do these continue? These wind speeds continue all the way down? What is the material that's deep inside? We know that most of Jupiter is in fact hydrogen with a little bit of helium. But then what else is there? Our ideas of how Jupiter formed involve a core of ice and rock material onto which hydrogen was pulled in by gravity. We don't know what it's really like inside. How is the magnetic field? Jupiter has a very strong magnetic field. How is that generated? Where is it generated? So there are lots of questions that we really don't know the answers to. And indeed, the main ones are, how much water is there inside? Oxygen being the third most abundant element in the universe, you would expect if you combine oxygen and hydrogen, what do you get? Water. So you'd think there'd be a lot of water inside Jupiter. We don't know how much there is. That's a key question. How did Jupiter form? How did our solar system form? How do other solar systems form? We're now finding many other solar systems. Is ours typical? Jupiter, being the most massive planet of our solar system, plays a big role, and so it's key to understand these questions. Now, what's important is to get up close, as I said, and we've chosen an orbit with Juno that is very special. There's a belt of very nasty material that is around, forms a big sort of donut around Jupiter. These are the radiation belts that are very nasty, very energetic electrons, MEV electrons, which you really don't want your sensitive electronics and detectors to fly through. So we've chosen an orbit which flies from pole to pole here very quickly. So we skim over the clouds underneath, duck under the radiation belts, and then go out again. These are 14-day orbits, so we have 2 hours to go from pole to pole very quickly, and then we spend the rest of the time sending the data back to Earth. Unfortunately, the orbits will naturally precess in a way, going from up here in orbit 1 down to about orbit 30 down here, and eventually we fear we will go into these radiation belts, but with a bit of luck we'll have many orbits before this happens. So this is the plan of what we're going to do. We've designed our spacecraft to protect itself against these radiation belts. We have all our electronics carefully kept in a vault, and we're powered by solar power. So these are solar panels, and for scale, here is a human. So these are really big. The Juno spacecraft would only just about fit into this room. It's huge. It's 60 foot or 20 meters across. We have a bunch of instruments. We have a magnetometer out on the end of the boom here. We use the radio antenna to communicate with Earth, but also to do some gravity science, to measure the motions of the spacecraft that produced by the gravity of the planet Jupiter. We measured charged particles with 2 particle instruments. We measure plasma waves, a UV and infrared spectrometer. We measure microwaves from the deep interior. And as you all know, microwaves are absorbed by water. And by measuring the amount of absorption of these microwaves, we can work out the amount of water inside. So this is what we're going to measure, a bunch of things. There's also a little camera that will be used to take some pictures. So this is the big question. What's it like inside? Do we have a core, or is in fact the material all mixed up inside? Current ideas are not clear what it's like, and that'll be important for understanding how the planet and indeed the solar system formed. So this is what we're going to do. We're going to fly over the poles. We're going to look at the bright auroras. We're going to measure the particles that bombard the atmosphere. And by looking at the gravity field and the magnetic field, we'll get a sense of what it's like inside. Is there a core, a central core, or is the material more distributed? What happens to hydrogen at the very high pressures at the center of Jupiter? So July, watch out for the orbit insertion, and then over the next 18 months or so, there will be data coming in, which I'm sure will be available. Now I want to move from the largest planet to one of the smallest, the dwarf planet, New Horizons. And you may have noticed that there was an important flyby that happened on the 14th of July last year. 14 Juillet, the Bastille Day. We like to have our orbital motions happen around major important holidays around the world. So this is an artist's picture of what of what Pluto might look like. And indeed, this is quite typical for the size of the moon Charon and for the brightness of the sun. And indeed, the surface seems to be covered with a lot of ice. So let's think a bit about Pluto. Pluto is out on the edge of the solar system. When it's closest to the sun, which was back in 1989, it was about 30 times the distance between the Earth and the sun. It was discovered back in 1930, back here by Clyde Tombaugh, and you can see that it's barely gone halfway around its orbit in the time since it was discovered, because it has a very long orbital period of 248 years. Now notice that there's also, I've mentioned here, the second Kuiper Belt object was discovered when Pluto was there. We'll come to that in a second. So the way that Pluto was discovered by Clyde Tombaugh was a young man. He was an intern at the Flagstaff Observatory, and he looked through the telescope and took pictures using photographic plates, big pieces of glass, and then he processed those and looked at them and tried to compare and look for objects that move relative to the stars. Now look at these two pictures and you tell me, can you see an object that has moved from one to the other? Can you see it? Yeah? Is it there? Okay. So it's hard to do this with photographic plates, and it took a long time before we saw more objects. In the meantime, a moon was discovered looking at these two photographic plates. You see there's something on the side, and what we found was there was a moon moving in front and behind. The moon Charon moving, which is about half the size of Pluto. So it's almost like a binary system with these Pluto and its moon Charon. Now we can use modern digital technologies, and this allows us to detect these objects that are moving relative to the stars quite easily. And here we've now detected over 1,000, maybe nearly 2,000 of these Kuiper Belt objects. This is the belt of objects in the outermost part of the solar system. They're very varied. Some of them are red, some of them are white, some of them are big, some of them are small. A whole bunch of them out there in the outer solar system. And here is a movie that shows you the discovery. So we have the orbits of Jupiter, Saturn, Uranus, and Neptune, and then here's Pluto. And then these are the objects that have been discovered since 1992. So relatively recently, these are the new objects that form this Kuiper Belt, a kind of asteroid belt of icy objects out beyond, pretty much beyond the orbit of Neptune. And Pluto is in fact the largest that we've found to date. So you'll also notice when this tips on its side that these objects are scattered away from the plane of the planets. And so this formed a very scattered collection of objects, the Kuiper Belt. So when we look at the Kuiper Belt, we have a bunch of different objects with kind of cool names. A lot of them have moons. But for comparison, let me show you Ceres. This is the size of Ceres relative to these objects. Another dwarf planet that NASA's Dawn mission recently took this picture of. And this is sort of what I thought Pluto would look like. Basically a big icy object with impact craters on it. So for size, here we have Pluto and its moon Charon. They're relatively close and they orbit in phase with each other with a 6.4 day orbital period, and they're phase locked, so one side is always facing the other, like our moon is locked to Earth's orbit or spin motion. Okay, so let's look at the Earth on the same scale. You can see that Pluto and Charon are really small, and the relative masses are quite big between Pluto and Charon, just a factor of 8 between them. But you can see that they're much smaller, 457 times smaller than the mass of the Earth. So these are indeed quite small objects. So this was the best that we could do from Earth, including the Hubble Space Telescope. And between 1930, when it was first detected, and the New Horizons flyby last July, this was the best that we could do. And you look at it and you say, oh yeah, I can see mountains, I can see valleys, I can see impact craters, right? No, you got brown splotches and light splotches, and that's about the best we can do. We did know a few things about these objects. We knew that their density was roughly twice that of water. That meant they were roughly half ice, half rock. And that we knew the surface temperature is about 40 Kelvin, that's minus 233 Celsius, or minus 390 Fahrenheit. I don't care what units you use, it's bloody cold. So we have ice on the surface. Pretty much everything is ice at those temperatures. We have darker areas and reddish areas, but we don't really know why or what's causing that. So what's it really like? Time to go explore. So back in 1989, when I was a young junior professor, this young man called Alan Stern, who was a graduate student, came to me and said, you know, with Voyager passing Neptune in the fall of 1989, that comes the end of an era of space exploration. We should send a mission to Pluto, the next object out. And I thought, well, okay, piddly little Pluto, you know, but what else do we do after Voyager? We got to do something. So I joined up in campaigning with him to NASA, and it took a long time. There were many studies. A lot of them got started by NASA, and then they sort of got cancelled because they ended up being too expensive or people didn't like them. But you'll notice that along the way, about halfway through all these studies, we began to discover the Kuiper Belt. And this meant that Pluto was not alone, and it served an important purpose of understanding not just this one object, but a class of objects. And we began to realize that this was important for understanding solar system formation. And indeed, in 2001, the New Horizons mission was selected to fly. So we had to propose to NASA, and notice there's only 2 women in this group. Remember that for later. We had to build the spacecraft, we had to test it, shake it, bake it, move it around so that when it got launched it would be fine. And then we had to decide what instruments to put on. So we put a long-range camera, we put a long-range camera, a short-range color camera, we put a UV instrument on, we put particle instruments on, we used the radio antenna to communicate with Earth and do some tests of the atmosphere. But the most important of them all is the student dust counter that was designed, built, tested, and operated by students at the University of Colorado. So if you're interested in working in space research, you want to do aerospace, you want to do space physics, you want to do planetary science, come to the University of Colorado and study there. Join our PhD program. Many of these students have gone on to be successful engineers. So the instrument that they built is about the size of a sort of standard tray that detects dust. It's very special pieces of plastic that collect when it goes bombarding, and the spacecraft is moving at 33,000 miles an hour. As the spacecraft goes through the solar system, rams into a piece of dust, it produces a signal, and we detect and count pieces of dust. Okay, so I've got to ask you all a question. How often do you think we ram into pieces of dust as we go out to Pluto? How often do you think we bash into a piece? So 100 times a second? 20 times a second? A billion times a second?
0.01.
0.01 every 10 seconds? Once a week? Guesses?
Once a year.
Once every 3 days. Who said once a day? Very good guess. Pretty good. Okay. Once every 3 days. What that means is space is pretty empty, right? So most of the dust has been cleared out, probably because of charging of the dust, which then causes it to spiral in towards the sun as it interacts with the solar wind. Okay. So we got ready for launch. Launch was in 2006. I'm looking around to see how many people are about anybody have their birthday on that day? We did have a whole bunch of people. There are a lot of people who are about that age. And so we launched, and great, off we go to Pluto. Except it was not so simple. Just before launch, and then soon after launch, we used the Hubble Space Telescope to look at the Pluto system. And we found there isn't just Pluto and Charon, but 4 more moons. So we now have 6 objects to look at. This has just got a lot more complicated. And if there's a bunch of moons, then maybe there's a lot more dust. And we got to worry about this dust hitting the spacecraft, not just the little pieces that we can collect with a student dust counter, but what about big chunks? You know, what if this is a bunch of debris there? We started to get worried. Okay, so we need to do a quick timeout to talk about why does this all matter? Who cares about the Kuiper Belt and Pluto? And the answer has to do with solar system formation. How do we get to be where we are? That's the Earth where it got to be. Then we need to understand how the solar system got to be the way it is. How did we go from a cloud of gas to make a proper solar system? The standard theory is that we have a big nebula of gas that collapses. It begins to spin up and form a disk, and that the sun forms at the center of this disk. So it's hot near this young sun, and only rocks and metals will condense out at those hot temperatures. So you end up, and there isn't a lot of rock and metal in the universe, and so we make quite small small planets in close to the sun. Further out, when it gets colder, you get beyond the frost line, there will be ices, particularly water ice, because oxygen is so abundant in the universe. We expect there to be a lot of water ice, making big snowballs onto which gravity pulls in hydrogen to make the giant planets. So this is our standard theory, to have small rocky planets in close to the sun, big gas giants further out. But what about the Kuiper Belt? Well, there were, a few years ago, some scientists began to realize that it's kind of difficult to make Jupiter and Saturn where they are. And so there's, not Jupiter and Saturn, sorry, Uranus and Neptune where they are right now. Right now, Uranus and Neptune are out here at 20 and 30 times the distance between the Earth and the Sun. And so they came up with an idea that let's put Uranus and Neptune in close with Jupiter and Saturn. Then let's have a bunch of small icy objects, which we'll call planetesimals. Those are planets in making. And then let's run this system through our computer, just using the gravitational interactions between these objects. And then let's see what happens. And what happens is that the Kuiper Belt objects, or the planetesimals, get kicked out. Yeah, that's going to make the Kuiper Belt. It's also going to bring water towards the Earth. And then at some point, kapowie, there is a resonance between Jupiter, Saturn, Uranus and Neptune that sends Uranus and Neptune out and scatters all these objects in towards the Earth and out towards the Kuiper Belt. So this idea of planetary migration, or there are many more, including scientists who work here at the University of Toronto on these dynamics, lots of theories about how we have these resonances moving things around and causing planets to migrate. And this really has been provoked by discovering there are a lot of planets around other stars that orbit very close to the Sun. So planetary migration has become an accepted idea in solar system formation. But this is very convenient because it puts Uranus and Neptune in their current orbits, it makes the Kuiper Belt, and maybe this is one way in which you can bring water to the Earth. So going to Pluto and exploring the Kuiper Belt is part of our testing these ideas. Okay, so we have a 9.5-year journey to get all the way out to Pluto, and so it's a long wait. And when we get there, we have a flyby of the system. The New Horizons spacecraft flies through here. And there are 3 very important facts that we have to think about. One is that we're moving at 33,000 miles an hour, okay, through this system, or about 14 kilometers a second. The second, and along with this, it means that 4 hours later to go through the system, right? So that's a really short time, right, after 9.5 years of getting there, okay. There's another important fact, which is that out at 33 times the distance between the Earth and the Sun, the communication time between the Earth and the New Horizons spacecraft is 4.5 hours. Okay, with a 4-hour flyby, we're not joysticking this spacecraft, right? because we can't communicate. By the time you tell it to move left, it will have already gone through the system, right, by the time it receives that signal. So this really is a robot. We're telling it what to do, it's going out there doing it, taking all the data, and then turning back to the Earth and telling us what it did, okay? Now, the other problem is that we have a relatively small antenna, and the transmission rate is 3 kilobits per second. Now, your typical phone is probably something like 50 megabits per second, right? And even with the slowest modem of the old days, we're better than this transmission. So it takes 18 months to get all of the data back from the spacecraft. Another factor is that we're so far away from the sun that the illumination of the planet is about 1,000 times less than the sunlight that we get here on Earth at noon. And so you can actually go to this. It's actually kind of cool app that you can use to go and find out what time of day is Pluto time, which is the time of day when the light is about right, equivalent to Pluto time. And so the light at Pluto, and so you can take a picture and post it if you like. But the consequence for the mission is that the exposures are quite long. Okay, when you want to take pictures of the planet, and so we don't want to get too close, otherwise the pictures will all be very smeared, and so that dictates how far away we have to be to take our pictures of Pluto. Okay, so you can use one of these online programs and look at the simulation of Pluto having pictures taken by the New Horizons spacecraft. New Horizons flying through the system, taking a bunch of pictures, looking a whole bunch of data, and you can see this is at 3 hours, nearly just under 3 hours before arrival. We're taking all these pictures. We had pictures better than Hubble several months out, but it really wasn't until we got up close that we really got the good pictures. That's again why we have to go there, is to get those pictures up close. And then we flew behind and went behind on the other side. Okay, so what do you do while you're waiting for the data to come down? Well, we took selfies, and this is the group of women who are on the team, and it's about a quarter of the team now, right? So at the beginning there were just a couple of us, and now you can see there's a whole team of women on the team, including the deputy project manager, deputy scientist, and the woman who did all of the talking with the spacecraft. Which I'll show you a picture. And this is Alice Bowman. This is her, the mission operations manager, or MOM as we called her. And what was great was at the end of the 14th of July, she announced that the spacecraft had indeed collected all the data, turned back to the Earth, and told us that the recorder, the solid state recorder, was full of data, and that's what we all wanted to hear. And so this was a great moment, similar to the July of 1969 when the Apollo astronauts landed on the moon, but you can tell from the outfits there's been quite a change in the cultural norms at Mission Control between these two eras. Okay, so what did we do? Well, I went nuts. I was so excited to see that we had all the data on board. Remember, I started working on this in 1989, and we didn't launch in 9.5 years of getting the spacecraft out there, so I was so pleased. And this is what we saw. A really amazing, I didn't expect it to be anything like as cool as this. I thought it was going to be this kind of really rather boring icy object. And look at this, all sorts of weird colors and shapes and forms. So let's go through some of these formations. We named them temporarily, that's informal at this point, it's not formalized, after various explorers, spacecraft, and some science fiction writers and heroes and villains and so on. You may recognize some of these names. So let's look at what we're looking at. Remember, we're with a 6.4 day spin period. We're only going to see one side. We've got 4 hours flyby. We're only going to see one side in detail, and so we chose the one with the biggest contrast And the heart, of course. Oh yes, we didn't know it had a heart until we were nearly there, so that was purely fortuitous. But we chose that side to look at in detail because we wanted to see where this dark region was close to the light region and what on earth is going on with the geology there. The pictures further away from this closest approach region will always be a little fuzzy. We're not going to get the best pictures from there. The best ones are going to be from the closest hemisphere that we flew by. Now we have to remember that what we're looking at is ice. And at these temperatures, water is very solid. It's like rock. Pluto is in fact about a third ice, 2/3 rock, and so the rock on the inside, ice on the outside, and it's very thick. Okay, so about 180 miles or 300 kilometers of water ice with a thin layer of nitrogen ice on the outside. So remember this, you're not looking at rock, you're looking at ice. So here we have a nice close-up picture, and you can see these structures over here are where water is acting like granite, making big mountains that are sticking up. And then we have softer ice, more like ice cream, where nitrogen and methane and CO are more fluid and can flow. They're still solid, but it's more like ice cream, or silly putty. If you leave silly putty out, it eventually flows outwards. So we know this is the composition because we use our spectral imager to look at different parts of the spectral, the part of the wavelength, different wavelengths. We know that CO and nitrogen and methane distributed, and you'll see a lot of it is in this region, which we're going to call Sputnik Planum, which is a huge big glacier. And then, but there are also places where there's fresh snow of particularly methane that seems to be changing with the seasons and moving from hemisphere to hemisphere. When we look at water, what we see is that most of the water ice is in fact in the darker areas, so some black stuff has accumulated on the water. Let's talk water ice. So again, water ice, very solid rather than liquid. So let's go and look at Sputnik Planum. This is the area where all of that nitrogen ice is. And we think when we look at topographic data, that is looking from stereo images, we can get a sense of topographic structures. And you'll see this when you get to look with the 3D glasses at the end of the talk. That probably Sputnik Planum is an oblique impact that made this huge elongated crater that was filled up with nitrogen ice. And when we zoom in closer, what we see is flowing ice, and you can see the stuff that's flown into off the edges here. And then in other places we see these polygonal cells. So these are convecting cells of nitrogen ice that are turning over. And this recent picture that was on the front cover of the Nature magazine recently, a couple of weeks ago, with an article by Bill McKinnon, where he analyzed these features that are really nitrogen ice turning over, convecting. And here is a simulation that he and his researchers made, where you have a turnover of material convecting, moving around these cells, making this pattern on the, as we think is on the surface in this Sputnik Planum. So it has a depth of about 4 kilometers and a turnover time of say 1 million years, which may seem a very long time, but geologically speaking that's very short, and indeed Sputnik Planum does not have any impact craters that we've found on the surface. So this convection system, which is obviously speeded up enormously in this movie, may be what's causing these cells here on the surface in Sputnik Planum. In between, what we see is debris. It's a bit like when you have soup and you heat it up and it turns over, and sometimes there's sort of scum that accumulates at the downwelling regions. And the scum in this case of Pluto is water ice, because indeed water ice floats, even though it's solid, it floats in the nitrogen ice. So this is a regime, these cold temperatures, of materials that we really don't have experience of here on Earth, or even in our lab. And so we're having to think about this in a very different way when we look at the geology of Pluto and try and compare it with things here on Earth. Sometimes we have analogies, and sometimes it's just darn different. So here's another region where we look on the edge of Sputnik Planum, and what we see are some big mountains. And these are mountains made out of water ice that stick up from the edge. And in fact, if we look at a topographic map, we see that these are several kilometers, 5-6 kilometers sticking up. So these are like the Rocky Mountains, but made out of water ice rather than rock. Here's another view where you can see the Sputnik Planum and these big convective cells with snow sort of accumulating on the top, and then the big mountains off to the side. We look at these older regions, we see impact craters, and we see cracks, tectonic features where the surface has cooled off and cracked. And then we see that there is snow, probably methane snow, that has accumulated on the top upper regions. And here's a zoom in, and you can really see where the upper higher regions, the edges of the impact craters, have been covered in this methane snow. So we flew into the system. We took lots of pictures of Pluto and Charon. We flew past, click, 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 took a lot of pictures, and then we went behind Pluto and looked back at the sun and saw the sun go sunset and rise again behind Pluto as we moved away from the sun. And this was very useful because what we did is we looked with our UV spectrometer to look back at Pluto and look at the sunlight, and this line shows the sunlight disappearing and then coming back up again. And this was very useful because as it gradually began to disappear and then come back up again, we could get a measure of the atmosphere. So Pluto has a very extended atmosphere of nitrogen gas, and we could measure this by using the occultation measurement with the UV instrument. We also looked back and saw hazes. These are aerosols in the outer layers of the atmosphere, so indeed Pluto's atmosphere is indeed blue, scattering, Rayleigh scattering. And what we think is happening here is that methane in the atmosphere is reacting with UV light from the sun, which turns it into hydrocarbons, ethylene and acetylene, which then accumulate furthermore and rain out. And we call this sort of dark, we've made this stuff in the lab, it's a sort of browny, orangey, yellowy, blacky, you know, it gets, as you accumulate more UV and make larger molecules, you end up with what we call tholins, which is the brown gunk that rains out of the atmosphere. So over millions of years, this material, the tholins, the photo products of sunlight on nitrogen, methane, and CO, produces this very dark region. So over time, the amount of tholins increase, whereas the young, fresh areas, or very white areas, are crater-free, are free of these tholins. So the amount of the darkness is an indication of how old the surface is. Okay, so they're passing around 3D glasses. You will get a chance to use them at the very end. Okay, so here we are. We have a fresh area here in Sputnik Planum with the fresh snow. We have old mountains. And if you look very carefully, you can begin to see areas where there may even be stratification, as if there's been accumulation of tholins followed by snow, which has made it white, and then more accumulation of tholins. So you see stripes of light and dark and light and dark, as if you're looking at a stratigraphic layer of rock that has formed in different layers. So we've got a long way to go in analyzing all this, but I think it's going to tell us about the seasonal and long-term geological variations of Pluto. And then we have these. What on earth could these be? These are holes. At least they look like holes. They are innies, not outies. And look at the scale. These are quite big. These are as big as this building. Could these be, you know, we're struggling to get a terrestrial analog. Could these be things like sun cups or penitentes, where you have snow that's been sitting out in sunlight for a long time? So at the end of a summer up in the Rocky Mountains, I know when you go up to the top of the mountains we can see these things, but that's just from one summer. What if you were exposed to a thick layer of ice that's been sitting there and exposed to this for millions of years? Maybe that's what's causing this. We don't really know. This is, again, out of our terrestrial experience. Here are more of these Pluto pits. You can see some whole patterns here. Why they're patterned like this, I don't know. They look a bit like fingerprints, don't they? Well, my group of colleagues, we study space physics. We don't do the geology stuff. We just sort of make up the geology and follow what the geologists say. Yes, geologists, no geologists. So we went in and we looked really close at these pits. We thought, well, you know, we studied space plasmas. We should be able to do this. And look what we found. Okay, the wonders of Photoshop. Okay, so the geologists did turn up with this one. What could this be? This is huge. You know, 100 miles across, big. Quite high. They call it an ice volcano, but I don't think we really know what an ice volcano is. It's clearly ice, water ice, sticking up, and maybe it is venting, or in the past has vented some kind of gas. Now, what could that gas be? Could it be nitrogen, methane, ammonia? We don't know. So lots of exotic things. We also saw these. What is this? It's called snake skin, we call it, because we don't know what else to call it. Very bizarre. These ridges are quite high, hundreds of meters high. And we really don't know why it could be this way, because if we use methane, which tends to be the thing that's circulating, it doesn't have the structural integrity to be like this. So there are all sorts of bizarre geology that we found in this environment that we don't really understand. So this is my favorite picture. And we see mountains over here, we see the flat Sputnik planum, we see the hazes of the atmosphere. Now, doesn't that look like a planet to you? Isn't that cool? I think it's just fantastic. And the illumination, you can see how it's illuminated, backlit by the haze in the atmosphere. So putting things together, here is a little animation showing the surface, and we'll do a skim down from the very top with the very icy layers of the northern hemisphere with impact craters and filled in with snow, sometimes exposed with dark stuff underneath. Those are those tholins. And then we come in over the big mountains on the edge of Sputnik planum, ice mountains sticking up with snow at the top. And then as we go further down, we go into Sputnik planum with the flat plains and layers of snow on top and ridges between the polygons. And then as we head down across Sputnik planum, we'll end up in the deep mountains below. So the geology of Pluto is quite extraordinary, and we're trying to understand what it's all about. Charon also has complex geology. It doesn't have an atmosphere. There was no absorption by gases outside Charon. This is mostly ice. It seems to be cracked. When it cooled off, it seems to have cracked open. And we have no idea what this dark stuff is at the North Pole. Maybe it's material that's migrated from Pluto. It can't come from the atmosphere because there's no atmosphere on Charon. So there are still mysteries associated with both Pluto and Charon. And then there are the moons, the small moons. We don't have very good pictures of them because they're so small. But what is very cool is we can look at their spins and their orbits. and just look at these moons spin. What is going on with Hydra, the blue one? Look at it. It spins nearly 90 times for one orbit. Very bizarre. So these two, Pluto and Charon, are in this very tightly coupled spin orbit resonance, but the other ones are going nuts. So I think this is going to keep the dynamicists, maybe the guys here at the University of Toronto, busy doing a bunch of calculations. And maybe if you're interested in a student project, this would be a good one to team up with one of the locals to go study what on earth is going on here. Okay, so what's next? After the flyby last year of Pluto in July of 2015, we're next going to fly on and fly past another Kuiper Belt object. We could only have enough fuel on board to move the spacecraft by about 2 degrees. So that's like 2 fingers held up like that. That's about 2 degrees. We could move it, and so we sent it off to a Kuiper Belt object that's technically called 2014 MU69. We called it Jim Green because that's the NASA official that we want to fund the continuation of the mission. And so we'll be flying past Jim Green on New Year's Eve of 2018-2019. So we should be seeing what that's like. And for comparison, here I am holding an exercise ball, and here about the size of a golf ball or ping pong ball is the size of Jim Green for comparison. So this really should be a primitive object that we'll be flying by and finding out what it's like and comparing it with Pluto. So this is really an amazing planet. It has all sorts of bizarre geology. We're learning how to do geology in an environment of very cold temperatures and very strange ices that we've not worked with in the lab here, let alone with our terrestrial experience. And I think it'll be a while yet before we really understand what's going on at Pluto. But it certainly is, has provided a lot of ideas about how these small objects of the outer solar system have formed and evolved, and is of course raising more questions than it answers. And with that, I'll thank you very much. Okay, so what I want to do is I want to show you some 3D pictures. So I'm going to bring up some 3D pictures, and you can put your 3D glasses on. And if you don't have a pair, you may have to share them. Have we got enough to go around, do you think?
I think
we do?
Everyone?
Okay. Okay, you photographers, you want to come up and take a picture of these people because this is so cool. And while you're looking at them, anybody have any questions?
Which eye?
Which eye? Oh, you need red on the left. It's not red on the right, it's red on the left. Yeah, I see a lot of people change that. Yes, far away.
You mentioned for Jupiter measuring microwave absorption to estimate the water.
Yeah.
I'm assuming you're measuring what doesn't get absorbed in order to do that. And then, so how do you know how much gets transmitted?
Okay, so the question is this: if we're going to use microwaves to measure the amount of water inside Jupiter, how do we do this? And while I answer that question, I'll move on to the next one. So Jupiter is a lot hotter inside. It in fact radiates out 2.5 times more energy than it receives from the sun, and some of that energy comes out as microwaves. And so what we'll do is we'll fly over and map out in 6 different wavelengths of the microwave spectrum the different absorption as we go over, mapping it out at these 6 different wavelengths. We'll have to use some modeling to get the complete answer, but we will be comparing at the different wavelengths. It'll tell us the amount of water and the amount of ammonia at different spatial locations as we fly over. Yeah, good question. Okay, are there any questions over at this side of the room? Yes, you, far away.
Just 2 small ones, but
We did find an object that was larger than Pluto in our solar. Was it in
Correction.
No.
Correction.
Oh, sorry, larger, yeah.
Eris was found, and Eris was found and thought to be bigger than Pluto for a while. But it's wrong. We now measure Pluto, and we now know Pluto is bigger than Eris. So, nah. Okay, second question.
Is there a clear distinction between the Oort cloud and the Kuiper belt, or is it a gradient?
Okay, is there a clear distinction between the Oort cloud and the Kuiper belt? And the answer is yes, by a huge amount of distance. So the Kuiper belt is between 30 and 50 times the distance between the Earth and the Sun, what we call an AU, astronomical unit. The Oort cloud, that's the Kuiper belt, in close. The Oort cloud is out at thousands of AU, okay? Much, much further. That's where all the little comets are. Must have been scattered at some point early on. And some of them come in occasionally. They get scattered, maybe by a passing star or something, and they come in. But they have very, very, very long orbits. But
it's clear in between.
it's a clear, well, we don't know. There's a few objects out there, but mostly clear, we think. Certainly the Kuiper belt drops off. Yeah, right back there.
Interrupt. If you guys have questions, there's microphones on each side, and so it might be better for everyone. So if you want to just line up at the microphones, if you have a question, then we can just bam, 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 go through them.
Okay, good. Okay, yes, far away.
Hi. So about those nitrogen convection cells,
Yep.
does that suggest that there's some kind of heat inside?
Okay, so what kind of heat do you need to drive them? You don't need much. Probably the radioactivity and primordial residual heat of the rock inside is enough to drive it. It doesn't take very much. You don't need a special additional heat source. Good question though.
Thanks.
Yeah. Next over here.
What do they think's inside the core of Jupiter?
What are the things inside the core of Jupiter? The problem is my colleagues who are on the Juno team keep changing their mind. Every time we have a team meeting, they give us a totally different story of what they think is going on. We used to think there were separate layers of rock, then ice, and then hydrogen, but that's not the case. They now say, just to give you another picture, they now say that in fact all of the water and the rock and so on would break up and dissolve in the hydrogen inside, and you just have separate atoms, so oxygen atoms, carbon atoms, nitrogen atoms, silicon atoms, and so on. We don't know, and hopefully Juno will tell us. Good question. Let's go over here.
I'm wondering if you can share a little bit of how your team decided, how your Juno team decided what the fate would be of that spacecraft, and what kind of goes into making that decision.
Okay, so what are we going to do at the end? Well, we change it. We first of all got to get into orbit. Let's get some data, then we'll be happy. We designed for 36 orbits, and hopefully it'll survive that long. And we currently have money for 36 orbits. If it keeps going and everything's great, we might keep going a bit longer if they give us more money. On the other hand, if the spacecraft really cannot survive because it's been radiated too much and the electronics are harmed, we've designed, it's planned to hit the planet, just go into the planet and burn up. So we don't know what the fate is. We'll see. Maybe keep going for a bit longer. Okay, if you want to ask a question, there's a microphone there. There's somebody over here. Go to the microphone. Okay, yeah.
So you mentioned that Pluto has like a nitrogen atmosphere.
Yep.
Yet Pluto, we all know, is smaller than the moon. So I guess the question now becomes like, how come the moon never actually retains its atmosphere?
Excellent. Okay, so the moon obviously is much closer to the sun. It's a lot hotter. And so any volatiles like nitrogen and methane and so on would evaporate and go away. Pluto is out where it's so cold that the amount of these ices, nitrogen, carbon monoxide, and methane, are solid, but they do evaporate. The vapor pressure there varies with temperature very strongly. And so in fact we think that as Pluto moves closer to the sun and further away from the sun, the amount of material in the atmosphere will condense down when it gets colder and evaporate when it gets further away. So it's a very dynamic atmosphere, if you like, on Pluto. Whereas our moon moon, any volatiles that were there, like water, have long since gone because it's too hot. Whereas the rock stays around because it's not that hot. Okay?
Thank you.
Okay. Okay, your question.
Yeah, I was wondering.
We got any more? We got, oh, look at this one. This one's the best. Sorry.
Since we were planning for Juno, I guess when New Horizons was still on voyage, are you guys planning the mission after Juno right now?
Okay, so what's next? So where do you think we should go? Europa! Yeah, we should go and look at that moon of Jupiter that has a thick layer of ice, and underneath that ice we know that there is liquid water underneath, and it's quite warm, and there could well be life there because it has heat, it probably has nutrients from the rocks below, and it's been hanging around for a long time. It's liquid water, so maybe there are whales swimming around. I don't know. We're going to get, Europa is the next target, and certainly there is a plan for NASA to go there, and ESA too wants to go to Europa. Everyone wants to go to Europa. It's the next cool place. Maybe Titan too, also cool. Okay, over there. Tell me when you get bored of this picture. We'll go back to the next.
Kind of like with Europa, is it possible there could be water underneath the surface of Pluto?
Ooh. Well, Bill McKinnon, the guy who wrote the paper in Nature about the convecting cells, he thinks there is. There could be. It'd be quite deep, though. I mean, remember that layer of ice is 300 kilometers, and you may have 20, 30 kilometers of water deep down. So it's not likely to be an easy place to get to, and it's probably going to be very cold. So I would not think Pluto as being very high on the list of places to go and look for life, if that was what you were after. Kind of, yeah. Okay, over here.
What technology do you think will have the most impact on the data gathering capabilities of these probes?
What future technology?
Yeah, that's being researched now.
Research now will go forward. A whole bunch of things. I think the most important is onboard data processing. One of the biggest problems is getting the data down, and if there's a way we can do onboard data processing, that will save us a lot of effort. I think making instruments smaller, lighter, more energy efficient will be hugely important for sending out small satellites. I would love to send not one spacecraft to Jupiter, but 20 spacecraft to Jupiter. And so we can map out the magnetic field and the charged particles that have come from the moon Io and become ionized and fill up the environment and all this sort of stuff. Sort of things that we do here at Earth with multiple spacecraft, we could do at Jupiter and Mars and let's go to Venus, our neighbor, right? We've hardly ever been there. So we have to design things that will survive heat, survive radiation. Lightweight instrumentation is the way to go. Yeah, good question. Yeah. Okay, one more. Ask away.
Someone mentioned about exploring Europa as possible candidate for life. I guess the other one people have floated around is having water is Enceladus.
Right.
I guess of the two, if you had to pick and choose only one, which one would be like the better candidate for exploring?
You can't pick one. Of course, we have to do everything.
Right,
the first one, probably the next priority is to go to Europa because it's one that we haven't been to in a while, and I think it's the most useful to get to. The thing about Enceladus, do you want me to go back a couple? Have a look at which one do you like best? This one? That one we were on, we'll go back again. Okay. The thing about Enceladus is it does have an active plume, and so if we could fly through that active plume, a geyser, we could measure the stuff that's coming out from below. So that would be really cool, but it's kind of difficult to do. It's not an easy experiment. On the other hand, I'd love to know what the brown gunk is on Europa. Yeah.
Do you think that they'll classify Pluto as a planet?
Excellent. Okay, so this is my standard response. Dwarf people are people. Dwarf planets are planets. I think it's a fake distinction. I mean, didn't it look like a planet to you? Yeah, of course it is. Who cares what the IAU says?
Well, I'm not really a spaceologist, but how far can we send something on our lifetime, I think? Like, what's the furthest we could really go?
Okay, so Voyager left Earth in the 2 Voyager spacecraft about when I was starting grad school in 1977. And those spacecraft are still leaving the solar system. We're talking to them out at 120 times the distance between the Earth and the Sun. And so that is 4 times further away than Pluto. So, you know, just in my adult life, we've gone 100 times, 120 times the distance between the Earth and the Sun. Then comes the question, could we, as some, I was going to say nutty US senator, I can say that, I'm in Canada, right, okay. A nutty US senator said, let's send micro satellites out to Alpha Centauri. The problem with that is there are 3 main things you need for space exploration: propulsion, power, and communication. And if you're doing a microsat, and I think he was talking about, you know, something the size of my fist, you can't power it, you can't propel it, and you can't communicate with it. So that isn't going to work. Somebody needs to teach him a few laws of physics. I think that we will be sending out spacecraft out to and find ways to go out to the Kuiper Belt a lot quicker, but it still takes years. We're not going to be traveling to the nearest star in our lifetime or even your grandchildren's lifetime. Let's be real. And we're certainly not sending humans. Okay, let me go back one more. How about this one? Okay, yeah, far away.
Will the instruments on Juno be collecting data on the Jovian moons as well?
Ah, good point. The problem is that Juno goes over the poles and it has this orbit that basically takes it out of the equator. And the moons are confined to the equator. So we don't get a very good view of them until the orbit begins to precess down, in which case we do cross the equator closer to the moons. The nominal mission, we don't get in quite as close as Europa. The problem is we also don't want to hit the moons because we may, Juno is probably carrying bugs from Earth and we don't want to carry them to Europa and infect the whales, okay? Planetary protection is a real issue. We will take some pictures, we will make some movies, but really wait for the Europa mission and the JUICE mission to get the best moons. Yeah, we'll do some, but I don't think the pictures will be that brilliant, to be honest with you. Okay, yeah.
I think you might have partially answered my question. You mentioned at the end of your Juno mission that you're planning to crash the probe into the planet, and I was wondering why.
Because we don't want to hit Europa. Okay, yeah.
All right, just a few more questions. So everyone's standing up right now. We'll finish through those people, and then we'll...
Okay, sure. Far away.
I'll better make my question work for that. So I remember back in the beginning, you showed that little animation of Neptune and Uranus kicking out the belt, how there was a temporary moment relative to cosmic time scales of instability that may have blown up. Basically, could that happen again in the future? Have the simulations been run far ahead in the future? See if that would be a second stage.
The very person to ask is here at the University of Toronto. I learned about this yesterday. Really cool. So, are you a student here?
Not here, but another university in Ontario.
Okay. Well, I'm not going to give it away, but maybe is the answer to that question. We don't know yet. They're working on it.
Who should we ask?
What with a local person? How do they find out what they don't know what the answer is yet. We don't know what the answer is. They haven't done the calculations, but they're trying to find out.
Cool, thanks.
Okay.
With propulsion systems, I guess we have a plasma engine that's going to come into play in 2017. Working on that. That would get something up there a lot quicker. Yes, and what's happening your wormhole technology.
Okay, so yes, there are plasma engines. I actually worked on Deep Space One that used a plasma engine. I think there is hope of other ways of propelling things. The other problem, though, is that you can accelerate for a long time and get somewhere, but then you have to slow down when you get there. So I also think that aerobraking, we should test the technology out at Venus and then also Titan to do aerobraking. You come in and do aero capture into the atmosphere. So I think there are technologies that will work. As for wormholes, I don't think so. Yeah, that movie was way, way off in the future. Fantasyland.
There seems to be a lot more chemistry happening.
Oh, yeah.
Oh,
yeah.
Frozen rock.
Yeah.
Is there organics happening up there, like amino acids or?
Okay, so yeah, I mean, can you go from tholons, things like acetylene and ethylene, into more complex things? We've seen some pretty complicated organics out in space, in interplanetary space. And so, yeah, I think they could well be. Now, does that mean these are just the building blocks for life? You're not going to get RNA and DNA, I think, in space or on Pluto, because Pluto's so cold it's hard to make. You kind of need to have water as a medium to make really complicated molecules occur. And you know, and we're thinking that life probably started deep in the oceans of the Earth. It could well be also happening in a similar or different way on Europa. That's why going and looking at an ocean like the ocean of Europa would be a cool place to go. I don't think you're going to find complex organics any more complex than those basic tholons on the surface of Pluto because it's so cold, but the chemistry deep inside the water oceans could be very interesting. Yeah, good point. Okay, last question for you, my dear.
So these 3D pictures are incredible, and I was wondering if we know what creates the many different textures on the surface.
Okay, so these textures are combinations. Let me go to the last one because that really is the best, right? This is a combinations of ice, water ice, which is acting like rock, sticks up. It gets broken up by tectonic features. When it cools, it cracks and breaks open. We have impact craters that are causing these big divots over here. You can see there's divots over here. And then the flatter stuff is flat, low viscosity or easily flowing methane, nitrogen, and CO ice. And so what we're learning is the geology and the physical processes that occur in a very different regime to the we have at the Earth. And so it's surprising that there's this much relief, indeed. But it's clear that it can happen. It's a low gravity environment. Remember, this is 450 times less massive than the Earth. And so the gravity on the surface is a lot weaker. And so you can have bigger relief with less gravity. But it's great fun, lots of cool stuff. Go and look at these pictures and tell us what's going on. Thank you very much. Sure, it's a pleasure.
Okay, everyone. So there's a couple things that have to be in order. So first and foremost, let's thank Fran one more time.
Sure, it's a pleasure.
So next, everyone who's wearing a red shirt, the volunteers, they had such an instrumental job in putting this all together. You definitely need to have without them. So please put your hands together for the volunteers as well. So if you see any volunteers outside tonight, then feel free to buy them a beer or anything like that. So now until about 10:30 or so, we actually have a number of exhibits still out on display outside. We have some telescope observing outside. So there's the moon out, there's Jupiter out, I think Mars is out as well, and I think it's clearing up. So